So now we come to the second part. In the first part, we have a very big overview of the Z transform and how is it used. In the second part, we're going to use the Z transform. Let's start with the simplest one first. I write the definition of the Z transform first. The Z transform of x of n, an infinite sequence, is simply this equation. And if I want to expand out for you, plus x of minus 1, z of, guys, let's follow. X of minus 1 is z of minus 1, okay? Plus x of 0, z of minus 0, plus x of 1, z of plus, can? Okay? Right, so from this equation, it is also one way to understand the Z transform. The Z transform converts a sequence to a polynomial of different power of Z. Okay? All right. Now, therefore, what is Z transform of delta n? What is delta n, guys? Everything is 0 except correct? So I substitute this into here. What do I get? Everything is 0 except 1, c minus 0. Everything is 0. Agree? And therefore, the Z transform of delta n equals to, so this is the first one, the simplest one. Can? Okay? What about slightly more complicated one? I love 1, 2, 3, huh? And I put the little arrow there, and what does it mean? So before that is all 0, huh? And therefore now this is 1, the Z transform, 1 Z 0 plus 2 what? Plus 3Z minus 2. Simply by inspection, yeah? So what is the interesting thing? The index is telling us what? The index of the Z tells us the time index. Can? Or I should say the negative time index. So minus 1 tells us minus 1, 1. Can? What does the coefficient tells us? The value at the time index, correct? So Z transform of a finite sequence. Why do I call this a finite sequence? Because everything else is 0, except some values. It's a very simple thing. He convert a finite sequence to a polynomial on the right-hand side. What is a polynomial? It's some function of some variable. In this case, the variable is z. Okay? And the coefficients are the original coefficients in the sequence. The time, the power of z shows us the position index in time. Okay? So the question now is Z transform a lossy compression or a lossless compression? Lossy or lossless transformation? Any loss in data? Yeah, lossless, because left-hand side and right-hand side can be reconstructed fully. All right, so I've given you two very simple cases. The discrete time delta n, finite sequence. When the sequence is very long, then what happens, guys? For example, zero, 1, 2, n. This guy is, for example, 1. This guy is half. So this sequence is xn equals to nothing before. What is the expression? Xn equals to? Yes. This is a causal or not causal sequence? Causal. Only right hand side. Can? Infinite or finite? Infinite in time. Infinite. So it never ends. Can I find the Z transform of Xn? And of course, you can write this equation. Right? You start with this. Agree? And then now you try. What should I write? Oh, you realize that the negative time is not interesting. So what do? We start from n equals to 0. Agree? And now, but even then, you have x0, z minus 0. And you still cannot end. Yes? And okay, you still say, I try. You write 1z. Second one is half. Third one is, yeah, half square. Yes? And you still cannot end. And at this expression is useless because there is no closed form. Yeah? Because it goes all the way to infinity. So we want to have a closed form. So typically, a table is given to you. And then you identify which is the xn. Can? And now, which is the xn? We are interested in. Which row? Number what? 1, 2, 3, 4, until 10. Number 3. an. A is half, right? Okay, so now let's go to the table. And number 3, say an un, and the Z transform is 1 over 1 minus a z minus 1. Agree? And then he got one more information here. For ROC. Agree? Can you see now? First, you go to number 3. Oh, ANUN. That is my time domain signal. Oh, this guy is my Z transform of XN, XZ. Remember, in the Z transform, we need one more information, the region of convergence. We'll come to that later on, but just take it from now. That absolute Z is greater than A. Okay? Now, when we reach here, what can we do? So I have now reached here. ANUN, the Z transform is 1 over 1 minus A Z minus 1, and the ROC is absolute value of Z greater than A. I now substitute my A to be half n UN, and therefore my Z transform is 1 minus half Z minus 1 greater than half. So far, okay? I have not changed a single thing, huh? And now, I don't like the negative power of Z. What do? I multiply both sides by, I multiply numerator and denominator. I get Z over Z minus half, right? And now, absolute value of Z is greater than half. This is, for example, let this guy be Hn. Typically, you all think this is Hn, okay? So, Hn becomes H of Z, and then now I can draw what? The unit circle again, the real part of Z, the imaginary part of Z, and I'm going to draw two things. The 0 is at where? Origin. And the pole is at half. And this point is at? And this point? minus j, j. That's it. Now again, we draw the pole zero diagram very, very quickly. Can you see? Okay? So now you understand this part. How do we use the Z transform? Typically, we use a table. We need the table for the Z transform pair as well as the ROC. So ROC, how do I do the ROC? He said that ROC for Z, absolute value of Z greater than half. So what do? I draw a circle, yeah, at half, right? So all this distance to the origin is half. Now I must draw my ROC. My ROC is greater than half. All this point, any of this hairy guy, his point to the origin is greater than half. Can you see? So now we use the ROC by drawing the region of convergence at our pole zero diagram. Please remember, every time you draw a pole zero diagram, you must draw the ROC. Otherwise, it's incomplete. So I haven't really tell you what is ROC yet. Okay, but never mind. Now, compare number 3 and number 4. You'll see a very interesting phenomena. Number 3 and number 4, h of z is the same. Okay? But the ROC is different. One is greater than A, means we draw the ROC external to A. The other one, ROC, is less than A. So it is a region, it is a circle that is inside A. So one is outside and one is inside. There is difference in ROC. It will generate for us different time sequence. One is a causal sequence, A to the power of n un. The other one is an anti-causal sequence, only exists at time step n equals to -1 to infinity. Okay? And so the take-home message of ROC is this. It will tell us whether the sequence is causal or anti-causal. Okay? All right. Okay, so I've just done this, and in my last slide today, we'll do the properties. Usually in more advanced courses, we will ask you to prove all the properties or more basic courses. Here we assume that you will know, and we are just going to use some of them. The most important one is linearity. Linearity means the Z transform of AXN plus BXN or BYN equals to AXZ plus B. Okay? That's it. That's what linearity tells us. Okay? The Z transform of the individual little part is the same as Z transform of the whole part. The other one that is important, so this is linearity. I didn't prove, we just used the principle. Z transform of xn minus 1 or xn minus k is equals to z minus k. Okay? So we have just used the time shifting property. And the last one we'll use is the convolution property. Is xz and now I should tell you, okay, we have done convolution, this is expression, and now you have to check all the ROC. Okay? ROC is in the last column of this table, and you realize that, okay, you have to do some mathematical operation on the ROC, such as the intersection of the ROC. That means when ROC exists for everybody, then the ROC exists. Now I'll just highlight using this very simple example of convolution. In this example of convolution, I want to show you why xn convolved with hn is the same as multiplication of the exact domain. So you can easily convolve 4, 5, and 1, 2, 3. You can also easily perform Z transform of a finite sequence. 4 and 5 converted to 4z to the power 0 plus 5z minus 1. H of n 1, 2, 3 becomes 1z0 plus 2z minus 1 plus 3z minus 2. So far okay? So this is trivial. Multiplication, also trivial, because xz and hz is very small polynomial. I can multiply together. Now, what? Observe the index of z. What do you think happened? The index of z helps us to shift the. So let's repeat. 4, 5 is converted to 4z0 plus 5z minus 1. Hn 1, 2, 3 is converted to 1z0 plus 2z minus 1 plus 3z minus 2. Xz multiplied by hz, you'll notice that the z to the power of 0, z to the power of 1, or z to the power minus 1 is going to help us shift the entire sequence, just like what I do in time domain. So I now multiply. Oh, 4z0 multiplied by hn. 5z minus 1 multiplied by hn. Exactly like what I do in discrete time, showing you hn is being delayed. Now getting my final yz equals to this operation. When I get this operation y of z, I can identify the coefficients and the power to tell me the inverse z transform, because 4 to the power of z0 is at time n equals to 0. 13z minus 1 is 13 at n equals to 1. 22z minus 2 is at 22 at n equals to 2. All right, and then it's done. So in this very simple example of closed form or very short sequences, we see that the z transform through the power index remembers time and make convolution like multiplication. Today, we'll go into the inverse Z transform. And the goal of the inverse Z transform is to find the sequence xn given x of z. And there are multiple methods to find. The first one is trivial. We have already seen that given x of z, that is a finite sequence. The coefficients power tells you the time index, and the coefficients themselves tell you the value at xn. The second one you have already done in the past is to do by partial fraction and convert it into a form of table, and then by inspection of the table, extract x of n with the corresponding region of convergence. So these are the two that you need to know for this course. In the third one, by long division, we'll never ask you to do. And in the fourth one, the contour integration, this is for theoretical purpose, and this is not in the course. So you need to do number 1 and 2 for the tutorials as well as the exam. We have already seen the inspection of a finite sequence of xz. Let us now see the partial fraction expansion, and what do we do? In here, we have already arrived and we have given you what is hz. And hz is a polynomial, numerator polynomial over a denominator polynomial, and in this example, it is negative power of z. We don't like negative power because we are going to do factorization. So what do? We multiply top and bottom by z squared. Therefore, converting it into positive power, and once we have converted into positive power, we know how to perform factorization. And once we have performed factorization, we can use partial fraction and break it down into simpler terms. You can look at the Khan Academy for the technique to break the expression into partial fractions. We'll now give you a simple example. In here, we have already shown you factorization. We have already made the denominator into factors. So is z minus 2 a factor, z minus 3 a factor? In this example, this slide shows you how to go from x of z in this form into a partial fraction form. So this is partial fraction. And then we use a table to do the inverse lookup to find x of n. So far okay, guys? And this you all know, right? I do not need to teach you. All right, so go through. Now, maybe this is the one thing that I want to highlight. In the partial fraction, it means that breaking your numerator-denominator polynomial into a form that looks like this. This form is an interesting form. We see that it is some coefficient divided by some factor. In this case, z is moved to the right-hand side, so it's z over z minus 2 multiplied by some coefficient. Z over z minus 2 has a inverse z transform, which is 2 to the power of n, okay, by the lookup table. So far, okay? You all know this? So, you have seen this before? All right, then that's it. Now, in here, you must be very careful. I have obtained the form from the region of convergence that is external, and therefore now I have a causal sequence, okay? So if you look at this sequence, is it exploding when n goes to infinity, guys? When n goes to infinity, what happens? 2 to the power of n. So this whole thing will blow up, okay? So this sequence is not stable, all right? Okay. So we have a difference equation. This is called a difference equation. And we want to perform z transform. And it is now what we always do. We convert z transform just by symbolic manipulation. We don't need to even understand z transform. We just think of it as a conversion from yn to y of z. The constant 4 over 3 remains. And here yn minus 1 becomes z minus 1 y of z minus 7 of 12. And yn minus 2 becomes z minus 2. So we realize now that the minus 2 here is to take care of the delayed version by 2 samples for y of n. And then now we have y of z plus 1 over 12 z minus 3 y of z plus, and then we have x of z minus z minus 3 x of z. Okay. And then you keep on manipulating so that now you have y of z on one side and you have x of z on the other side. And then what happened, guys? What's the next step we're interested in? We're interested in h of z. And h of z is, and now you get something on top divided by something below. So we call this the numerator polynomial the denominator of z. Right? You have two polynomial, yes? And now I'll show it to you now. And we have reached here. H of z equals to y of z, they are x of z, and we have a numerator divided by a denominator. Now we again don't like z minus, so normally I multiply by z cubed, because on top z cubed, and then I can factorize. Here, in this Fessler, he know how to do it in negative power, so he just do it, okay? But if you all don't know, normally I convert into positive power. And then from here to here, this step is called, yes, partial fraction expansion. And now you look at this, this is exactly the table form that we can use, and we find u of this one. This guy is this guy, this guy is this guy, this guy is this guy. All right? It's a lookup. Can? And then we can solve. So again, you realize that once we have done this, the next step, okay, logically is from h of z by partial fraction. By partial fraction, we'll express it in some lookup table. Yeah, the form that is like lookup table, and then this is h of z, and one more, inverse z transform, we get in discrete time. Here is still in the z domain. Okay? So now you can see the full process. Huh? From yn, which is a difference equation, we get y of z. The whole purpose of getting y of z is to get, in this example, h of z. The whole purpose of getting h of z is so that we can express it in this form, and then in partial fraction, and then to use inverse z transform to get h of n. Let us draw a block diagram. And we are going to do x of n, y of n. Agree so far? And then next one, we are going to do minus x n minus 3. So this is z minus 1, z minus 1. So this is x of n minus 1, x of n minus 2, x of n minus 3. So now we have reached x of n minus 3, passing through 3 brackets, yeah, 3 delay box. And now we multiply by minus 1. And then now we sum. Okay? And now we want to get y n minus 1 multiplied by how much, guys? Yes. And then the next one, yn minus 2 multiplied by, and one more, the last one. Okay, and this guy is called direct form 1. Okay, we have clearly shown from here to here, and once from here, remember in tutorial classes, if I want to find the impulse response, I send an impulse. And I will tell you the system is relaxed, means all the memory here are 0. And then you fire the impulse and you simulate by brute force and generate h of n. But if you do that, you can only find that you can list a few numbers, 5 numbers, 10 numbers, 100 numbers. And you realize that if I ask you for the closed form solution, the closed form solution means the equation telling me h of n to infinity, then the equation is here. Okay?